All right, let's look at the other two systems showing up in your application problems, 4 and 5. And I'm not going to go into so much detail for these, just make a couple of comments. And mostly, I think, you have enough to explore these ideas on your own. So this is one of these chemostat problem type setups where you have some perfectly stirred tanks with some stuff in them. It doesn't matter what the stuff is, some chemical. You can imagine that it's salt if you want to. For this problem, I recommend keeping track of units. I think that really helps to make sure that you're on the right track. So even though there are no units, I just use the word volumetric flow rate, but I don't say what are the units of volume or what's the units of time. You can just fill in units, just be consistent, just to help you think about it. So for time, imagine minutes or seconds or something, pick one. For volume, imagine liters or meters cubed maybe. So you've got these two tanks, and they have some volumes, V1, V2, and there's your liquid with some chemical in the liquid, so water with salt in it or something like that. And you've got a pipe and another pipe and some pump, and liquid is being pumped this way and this way at the same rate. So we say, in this problem, I'm using a little q here for the volumetric flow rate. So that means the volume of stuff, of total liquid per unit time that's being transferred. So since it's the same flow rate, the total volumes are not changing. So these are constants. V1 and V2 are constants here. But if you start out with different concentrations in the tanks, then as you mix between them, then the concentrations should change in time. So if this is tank 1 and has concentration C1 of T, that's a function of time. C2 is a function of time. And yeah, if stuff from tank 1 is going into tank 2, then the rate of change of the concentration in tank 2 is going to depend on the current concentration in tank 1. And similarly, the other way around. So this will lead to a coupled system of differential equations. Now, it's been a while since we did the chemostat problems earlier in the quarter with just one tank. But I'll just remind you that it all came from conservation of mass. So if you want to get the differential equation, it's a general sort of conservation of something type of differential equation, where you just say, the rate of change of the amount of stuff equals the rate at which the stuff is coming in minus the rate at which the stuff is going out. And just make sure you're clear on the units everywhere so that you don't write something nonsensical. And this is pretty much going to work. So that's like conservation of the amount of stuff. In your case, the amount of stuff is the amount of chemical. So you see how this is set up for you on the left-hand side? C1 V1 is the amount of chemical or salt or whatever it is that is in tank number 1. So ddt of that should be the rate at which stuff is coming in minus the rate at which stuff is going out. Then, I think the rest you can figure out on your own. So let's look at problem 5 now. Okay, so don't be too scared if you are not used to or not good at analyzing circuits. I'm not particularly good at this either. But I think I have put enough explanation in this problem to sort of teach you how to do it along the way. And it still leaves you with a bit of an interesting puzzle. So, okay, so we've got a circuit, and what's different about this is that it's not one loop, it's 2 loops. For some reason, this loop is drawn triangular shaped, but it doesn't matter. You can draw them as 2 squares. That's not relevant to the circuit. So the point is this is 2 loops, and there's a wire joining the loops in the middle. So if we had 2 separated loops, then we could write down, as we've been doing before, individual second-order differential equations for those, well, second order if there's an inductor, for those individual loops. But with them connected, you're going to get a coupled system of differential equations. So previously, how did you handle the individual loops and write down differential equations for those? Well, you would use Kirchhoff's voltage law. So that was the idea of conservation of energy. So I remind you about that here. That's just the sum of the voltages across the components around the loop should be 0. And to understand how to apply this law, so this law will lead to a differential equation. To understand how to apply this law, you need to know how to get the voltage across a circuit component. So, like say I'm going around this loop. The voltage as I go around this loop across each component, if I add up all the voltage drops across the components, I should get 0. But to know how to use the law, I need to understand what is the voltage drop across a resistor? What is the voltage drop across a capacitor? If I can figure those out, then add those, set it equal to 0. There's one of my equations. I have 2 loops here, so when I apply Kirchhoff's voltage law to each loop, I will get an equation. Okay, but you may have forgotten by now how to get the voltage drops across individual components. You can check in the book, or I hope that the notes I'm giving you here are enough to remind you how that works. So for example, you would use Ohm's law for the resistor, and so on. Okay, but to use these laws, often you need to have some notation for the current. And each sort of connected continuous wire part is going to have its own possible current. So like starting from here, running all the way up to here, that will have its own current at any given time. And that's a dynamical part of the circuit that can change over time. So here, this is the same picture, but with the currents given some notation. So we're going to call the current here that I was pointing out I2. That's a function of time, I2 of t. And then this wire piece I3, and then this wire piece here and there, I. So that's just the notation we're picking. And we now need a new law that we have not discussed before, which is Kirchhoff's current law. And that will help us relate the different currents here. So previously we have not had to discuss that because we would only have one wire piece, and so just this one current variable to worry about. So now, if you want to enforce that charge is conserved, that no charge is created or destroyed anywhere in the circuit, the current going into a junction should always equal the current leaving the junction. There are 2 junctions here. This one, this is the junctions are like a wire coming in and meeting some more than one wire segment. So there are 2 junctions, this one and this one. And if you write down that equation, that the current going in equals the current leaving, then you get an equation for this junction and an equation for this junction. But when you look at it, you find they're actually the same equation. You get this equation. Okay, so when you do this problem, you can kind of follow the guide, and your goal is to write these 2, the 2 equations that you get for Kirchhoff's voltage law for each loop. So fill in what the terms in the brackets, what you think they are based on the discussion. And then the goal, okay, there's this variable v getting used. What is that? Do I ever define that? Ah, yes. Okay, v is the voltage across the capacitor. So we just sort of picked the voltage across one random thing to be something we might be interested in. So we've got v of t and we've got I of t. That's this one, which we could have called I1. So we have I1, I2, I3, but we just called it I. I'm just suggesting that we focus on that. So we picked 2 things to focus on. It didn't have to be these 2, but we just picked these 2. So v of t and I of t. I is the current through this segment. V is the voltage from here to there. The voltage difference from here to there. So in the end, your goal is to write down a differential equation, system of differential equations in the unknown functions I and v. So you don't want to put in any other unknown functions here. So for example, I2 of t, that's an unknown function of time. You don't want that to be here. You only want to write in things involving I and v and the various constants like L, C, and R1 and R2. So one challenge you'll face here is when you initially write down these things, when you just fill in what goes into the brackets, you're going to have, like say you put in voltage across R1, that's I2 R1, right? That has I2, this function of t, I2 of t, showing up. So that's not going to be good for trying to write down a differential equation system that only involves these two unknown functions, I and v. It would have a third unknown function. So you have to use the relationships. So you might think, well, I can get rid of I2 because I2 is I minus I3, according to Kirchhoff's current law. Okay, well, that's good. We do favor having I rather than I2, but now you've introduced I3. So how do you deal with that? Okay, but then you can look in other places to see how you can write I3 in other ways. Okay, so hopefully that will be a fun puzzle, and I'm hoping that I've set it up so that the puzzling aspect is more just working with equations rather than having to worry about understanding how circuits actually work, which is honestly not something I understand either. Okay, and the fun parts are down here where you figure out, like, oh, if I set the resistor to below or above this value, then I can get oscillations or not get oscillations, and it's just cool to be able to figure these things out without actually having to go all the way down to a general solution, just being able to figure these things out by understanding the linear algebra.